actually going to move to start the proof of the Mordell-Weil theorem. I hope I could run here like the 20th Century Fox Funfair or something, but I think they would knock the video down on YouTube. So we'll just do it. All right. So we're going to prove the Mordell-Weil theorem. Let me first give you an overview of what happened, how was this proved. So the Mordell-Weil theorem is named after Louis Mordell and André Weil. Mordell proved it. So the Mordell-Weil theorem, as we know it, was conjecture. I believe Poincaré was pretty sure that this was true, so it was assumed to be true by Poincaré, and then Mordell proved it. Mordell proved it over Q in 1922, and then Weil proved it over number fields, which is the version we're going to prove, but he proved more than that. So the version by Weil is for any abelian variety. Abelian varieties meaning the elliptic curves are the one-dimensional case of abelian varieties. Abelian varieties are algebraic varieties with a group structure given by rational functions. And so over abelian varieties, over number fields, so for abelian varieties over number of fields was proved by Weil in 1928. Okay, so what did they prove? The proof. So what they prove is so let E over K be an elliptic curve. Then EK, the K rational points on the elliptic curve. Oh, I should have where K is a number field. Okay, let's rearrange this a little bit. Then EK is a finitely generated abelian group. What that means is that there is finitely many points that geometrically, with our addition law, these finitely many points are going to generate the entire group. So yeah, so you can write it like that if you want. So i.e. E over K is generated as a Z, as an abelian group by some finitely many finitely many points. So it's for some points Pi and Ek. That doesn't mean that all of those are of infinite order. Some of them will be finite order, some will not be. Okay, but if you've had a course in abstract algebra, then you know that, or a graduate course in abstract algebra, you hopefully arrive to the classification of finitely generated abelian groups. So the classification or finitely generated abelian groups tells you that a finitely generated abelian group can be decomposed as a torsion subgroup and a few copies of the integers. Okay, where EK torsion is a finite subgroup formed by points of finite order, and REK is a non-negative integer, so it's 0 or positive, called the rank. of E over K. Okay, we might say at some point that R is the rank as a Z module of EK. All right, so this is what we want to prove. And I want to give you an overview first of how we are going to do this. We're going to do this in 2 steps. This is the Mordell-Weil theorem, and this is the strategy. We are going to prove first what we call the weak Mordellvey theorem. So the weak Mordellvey theorem says that, well, if you have, if you go back, if this is finitely generated, so given this structure, what's going to happen if I mod out E modulo M times E, M some integer bigger or equal to 2, E modulo M times E is going to be a finite group. Okay, so note, so first, before I state the weak Mordell-Weil theorem, that if E over K is isomorphic to, I'm going to call it just T here, the torsion subgroup. If E is a finite group plus R copies of the integers, then for any M bigger or equal to 2, E over K modulo E M times E over K is T mod MT plus Z mod MZ to the R is finite. Okay, so if we have finite generation, then we have a finite group, right? So the weak Mordell-Weil theorem is going to prove that E mod M is finite. Okay, so we're going to first prove that. So the weak Mordell-Weil theorem is going to tell us that, so if K is a number field, and M is an integer, then EK modulo MEK is a finite group. Okay, so that is going to be the first part, which is what we call the weak Mordell-Weil theorem. And second, we're going to prove what's called the descent procedure. And this is just a group theoretic proposition that is going to say the following: let A be an abelian group, and with a reasonable notion of a height function. We will work on heights later on with a height function. Okay, so what that says is that a height function is going to be some function that tells me that I have points, and whenever I do multiples of points, the height increases. So it has to have that property that the height of multiples of a point is larger height. So just look at in the integers, there is a height, which is the size of the integer. 3, if you double it, 6, it has a higher height, and so on. And second property that we want is that there is only finitely many elements up to a given height. Okay, so there is just, if you think about it, that's sort of like what we want, that there is a finite number of generators of a small height, and everything else, it just grows in height. So there's only going to be finitely many points of a given height. Okay, so two properties. There's actually three properties, but let me just say two properties. The height grows with multiples, and only finitely many points of a bounded height. So that's with what I mean by a reasonable height function. And suppose that there is a height function and there is one m. The Weak-Mordellvey theorem says that for every m, the quotient E mod m is finite. But for the descent procedure, we just need, there is one m such that A over MA is finite. Then A is finitely generated. So it is a finitely generated abelian group. Okay. So what we want to do now is prove the Weak-Mordellvey theorem and then prove the descent procedure. The cool part about this is that you see that in the quotient, when I do a quotient of E mod m, if I know that E is like this, we will see, so the hard part, we will be able to compute the torsion group, no problem. We already know some things about it, about the fact that some of the, at least almost all the points are integral and so on. The hard part is getting your hands on the R. But you see that the R survives quotients. When you do E mod m, you have a torsion modulo m, whatever, I can compute that, no problem. But in this finite group, there are R copies of Z mod m. If I am able to get my hands on the copies and the number of copies, then I have a bound for the rank. And this will be a problem in the homework, which is a problem in Silverman's book, which is we're going to do the proof of the Weak-Mordellvey theorem, and then we're going to do it again, just trying to keep track of what is R in the proof. The proof is going to give me a bound for this R, and that bound is actually going to give me a bound on the rank of an elliptic curve, which is pretty amazing. So, which is that is nice. So look forward to that. All right. So this is the plan. So we're going to get started. All right. So let me get started with notation. Notation for number fields. We had all sorts of notation for local fields. So now we need the same thing, but for a number field. So K is going to be a number field. You know, if you want to keep in mind that you're working over Q, that's fine. Just work over Q, and K then is Q. However, we are going to have to extend our field at some point. So might as well start with a number field, because we're going to extend it a little bit before we can prove anything. MK is going to be a complete set of inequivalent absolute values on K. So if you know about Ostrowski's theorem, then you know what are the absolute values of a number field. For example, what are the possible absolute values over Q is the Euclidean absolute value or p-adic absolute values, and that's it. And over number fields is the same thing. There is the Archimedean absolute values, which come from embeddings into the real and the complex numbers, and then take absolute value or complex norm, or there are the p-adic absolute values. So then there are two subsets of MK. First, there is what we call MK infinity, which are the infinite places. So they are Archimedean absolute values on K. So there are, so K is going to be a number field of degree R1 plus 2R2, And then what that means is that there are R1 embeddings into R1, which give me absolute values that way, depending on how I embed into the real numbers and then take the real absolute value. Or I can embed it into the complex numbers in two R2 ways. They always come in complex pairs, but as an absolute value, those are equivalent, absolute values that you get, because you embed into the complex numbers and then you can do that one or the complex conjugate of that. So it comes in complex pairs. But there is a theorem that tells you that R1, the number of real embeddings plus 2 times the number of complex embeddings is the degree of the field. Okay, so those are those. And then there is the non-Archimedean absolute values. And those come from primes. Okay, so if you have a prime ideal in the ring of integers, then there is an absolute value attached to that prime, which is 1 over p. So this prime will be above one prime number p, and just take the valuation of alpha. That is, if alpha is an integer, then that is the so alpha will be in some multiple of so if you do this p-adically, then alpha will be in some power of the prime ideal, and that gives you the valuation of alpha. All right, and then we're going to write nu of x is going to be minus the logarithm of the absolute value of x according to nu for absolute values nu in mk, and the ord is going to be the normalized valuation for nu and for a non-Archimedean absolute value. Normalized so that the ord goes, the possible valuations are the integers. That's what normalized means. So that, yeah, so that you have a uniformizer, then the valuation, the order at nu of a uniformizer is 1. Okay. What else do I need? I'm going to write R. I'm not going to have a lot of space here, so I'm going to move to the next page. I'm going to write R, or I think Silverman writes R for the ring of integers, but most of the times I write OK for the ring of integers of K, so you might see that come up. So just in case, R or OK is the ring of integers of K. And remember that in terms of valuations, this is the numbers in K that the valuation is bigger or equal to 0 for all the valuations, all non-Archimedean valuations. Then we have the units. So the unit group of the ring of integers will be elements of K such that the valuation is 0 for all the valuations and non-Archimedean valuations. Then we're going to talk about S integers, and S integers means that we are allowing some denominator. So I'm not going to so the RS. So if S, we'll get there. But we will talk about S integers also, in that we allow a few denominators from a finite set S. Then we're going to complete at places, so just so we can use our stuff from local fields. For every place nu, I can write the completion of K add new for new in MK. For example, over Q, I have if nu is P a prime, a regular prime, then the completion is QP. If nu is the infinite valuation, the Euclidean absolute value, then the completion is the reals. And then in here, we have the typical ring of integers, maximal ideal, and so on, that we used to call KRM little k, but here, because now there is different valuations, we are going to decorate it with the place. Okay, so those are the usual ring of integers in the completion, the maximal ideal, and the residue field. Great. So again, so now our goal is the weak Mordellvey theorem. And it is the following. So if K is a number field and E over K is an elliptic curve, then for every m bigger or equal to 2, the quotient is finite. All right. And the first thing we're going to prove is a lemma, which is that I can actually extend K by a finite extension and prove it in the finite extension. If I prove it in the finite extension, then it's true also in the smaller field. So what we're going to need is the following lemma, which is that if L over K is finite Galois, and if E over L modulo M times E over L is finite, then EK over MEK is finite. Okay. So we are going to increase our number field if needed for convenience. What we're actually going to need for our convenience is to make sure that the M torsion is completely defined over the number field. And you know that, for example, over Q, that only happens if M equals to 2. So for example, even in the case of Q, if you want to do the Mordellvey theorem, you can do it with M equals to 2, and that works. But if M was 3, for example, then you would have to increase the number field. There's going to be also a couple of homework problems that are going to be about the proof of the Mordellvey theorem, so you understand what these extensions that are going to appear in a moment, what those extensions are about. Okay, and why the theorem is true for those extensions. The things we assume and we prove are going to be it's going to be a little more clear if you do those exercises. So here's the proof of the lemma. So we're going to call capital Phi is going to be the kernel of the map. There is certainly a map that goes from EK to modulo MEK to EL modulo MEL. That's simply inclusion. If you have a point defined over K, it is defined over L, so just throw it in there and see what happens. We're going to find this kernel. If this kernel is finite, then if EL mod MEL is finite, then EK mod MEK is finite. Okay, so note these fit in the following sequence. So if if this one is finite, if this is finite, then the 1 over k is finite. So if, let me write, if this and the kernel is finite, then the 1 over k is finite. That's a mess. So i.e., if the kernel is finite and E over L, M E over L is finite, then E K M E K is finite. You can just use the isomorphism theorem that EK mod MEK modulo the kernel has to be isomorphic to that. If this is finite and what you're modding out by is finite, then EK over MEK is finite. Okay, great. So so what we need to check then is that, so this is what we need to prove. That kernel is finite. Great. So for each P in the kernel, by the way, what is the kernel? The kernel are those elements of K that are not, well, that are, if it's 0, it's 0, but if that are not M multiples modulo K, but when I send it to L, it becomes an M multiple, right? So the kernel are precisely points in K intersect things that are multiples of M over L, modulo M multiples over K. Okay, so if P is in the kernel, we can choose is also a multiple of M over L. So we can choose a point for each P in EL with, yeah, that it is over L, it looks like a multiple of M. Okay, and with that in mind, we then can define a map of sets. A map of sets, lambda for each P. This is the Galois group. Maybe I should write it down. The extension was assumed to be Galois, so it's the Galois group of L over K to EM that sends sigma to QP sigma minus QP. Okay, so let me write this down again. So so for P and the kernel, there is QP and EL such that M times QP is P, and we defined lambda P from the Galois group to EM, sending sigma to QP sigma minus QP. That's sigma acting on QP minus QP. Let's check that this is in fact well defined. So I need to check that lambda P of sigma is actually an M torsion point. So what happens if I do M times QP sigma minus QP? The multiplication by M is defined over the base field over K. So a Galois automorphism that fixes K, it will commute with multiplication by M. So this is multiplication by M QP, all acting on sigma acting on quantity minus m times qp. And those are both p. So this is p sigma minus p, but p is defined over k. So this is O. Here, m multiplication by m is defined over k, so it commutes with sigma. And here I'm using that p itself is over k, so it's fixed by an automorphism that fixes k. So that is O. So therefore, we have a well-defined map of sets, Galois to EM. This is not a homomorphism, but it almost homomorphism. It was called a twisted homomorphism, which should give you a hint that there is some cohomology happening here. Okay, so we have not introduced cohomology yet, but this is what cohomology does. So whenever there's twisted homomorphism, something cohomological is happening. And we will go back after we've actually proved the Mordellvey theorem, then we will introduce cohomology and we will see what's happening in cohomological sense later on. But I don't want to, the thing with cohomology is that it's some huge canon that this would be proved very easily, but then it's sort of like a black box that you are not going to follow, like why was it true? All right, so so now what I want to prove that is actually that this map from points P to these maps, that is injective. So now suppose that this map is the same that another map for some other P prime. So for P and P prime that come from the kernel, phi. Then, well, I would have that QP sigma minus QP is the same that QP prime sigma minus QP prime, which if I rearrange, this looks like QP minus QP prime sigma equals QP minus QP prime for all sigma. But if this happens for all sigma, by Galois theory, the only things that are fixed by every automorphism are the things that are in the base field. So this proves that QP minus QP prime would be in the base field, and therefore P minus P prime, which is MQP minus MQP prime, is in fact not just in, let me actually write one more. So if I pull out, if I do a common factor of the QP of the multiplication by M, then you see that we've proved that QP minus QP prime is in EK, so this would actually be in MEK. But then that tells you that because the map, the kernel is modulo MEK, and that would give me that P would have to be congruent to P prime modulo MEK. So the upshot is that 2 points from the kernel, if they give you the same map, lambda, then they have to be congruent modulo MEK. So what I get is a map from phi to maps as sets from GLK down to EM that sends P to lambda P that is 1 to 1. Okay, but you see this is finite because it's a Galois extension. It's a finite Galois extension, so the Galois group is finite. This is finite, is of size m squared, and therefore the possible maps from a finite set to a finite set is just a finite set itself. Okay, but since phi injects it to a finite set, then that tells you that phi itself is finite, which is what we wanted to prove, because the kernel of the injection of ek mod m into el mod m, the kernel is finite, and we're done. Okay, so that is the first part. What we've proved is that we can extend our field by a Galois extension, a finite Galois extension, and we would be fine. So what we are actually, the way we're going to use that, we're going to use the lemma right away, because K adjoint the M torsion over K, this is Galois, is a finite Galois extension. You can reason this, that if you have any point of M torsion, the conjugates are also points of M torsion. Okay, so for example, if Q is a point of M torsion, then Q sigma is another point of M torsion, because of what we just saw, that the multiplication by M is defined over K, so it commutes with automorphisms. So this is for all, in fact, for all automorphisms of K bar, that's going to be true. And therefore, KEM contains all the possible conjugates of elements of that extension, and that shows you that the extension is Galois. That this extension, which contains all the possible M torsion points, is Galois. And it is finite because the kernel only has M squared points. So you just have to adjoin the coordinates of M squared points, and therefore it's finite. The degree of M is M squared, tells you that K over EM K is finite. And therefore, we can, by using the lemma, we can assume that the M torsion is completely defined over my base number field, or if it is not, replace K by K adjoint EM, which is a finite Galois extension of K. Okay, so we're going to assume from now on that the M torsion is defined over K. Okay, that is already an assumption. Say Z over Q, that is an assumption. We are already leaving Q. If M is bigger than 2, we have to increase the number field to make this happen. Right, so I have another about 15 minutes. So what I'm going to do now is define the Coomer pairing and perhaps start proving some properties of the Coomer pairing. So we're going to define a new pairing. So we're going to define, remember we had a pairing, which was the Vey pairing. Now the Coomer pairing, which is also very much related to homology, very much related to what we just did, is going to give us a few properties that are going to be key to prove the weak Mordellvey theorem. So here is the Coomer pairing is a pairing kappa from EK cross the Galois group of K bar over K to EM, we're going to find the left kernel and the right kernel to make this what's actually called technically a perfect pairing. But for now, just from EK cross the absolute Galois group to M torsion, and here is defined as follows. So for a point over K, we're going to choose a point Q over K bar such that multiplication by M times Q gives you P. Remember that the M map is a morphism that is not constant, so it's surjective. So there's definitely, for every P, there is a Q such that M times Q equals P. And then we define kappa of P and sigma to be Q sigma minus Q. Okay, so that's how we define the pairing. Let me actually, can I copy this? Oops, no, not like that. Oh, that's not what I wanted. Okay, never mind. I'm not going to figure that out live. So again, we have a pairing from EK cross the absolute Galois group to EM that sends P sigma to Q sigma minus Q, where M times Q is P. Okay, so there's a few things that we need to check. First of all, you need to check that this thing is well defined. There's two things here. We need to check that the image is a point of order M, which is that we've already seen. And we need to check that it does not depend on what I choose for Q. There's M square preimages of P. So I have to make sure that whatever I pick, it's the same result. The pairing is actually going to be bilinear. The pairing on the left, the kernel on the left. So the kernel on the left means elements that no matter what you put in the right would go to 0. So the kernel on the left is MEK. And the kernel on the right is a subgroup of the Galois group, which is automorphisms that fix L. Here, L is going to appear a lot, so we're just going to call it L. Whenever I say an extension L of K, it's going to refer to specifically to this field in the proof of the weak Mordellvey theorem, which is the field of definition of all the M preimages of EK. Okay, so for example, Q above is in this field. So take any element of K, do a preimage through multiplication by M, so a Q such that the M times Q equals P, then the field of definition of that Q, that is in L. And L is going to be the field of definition of all the preimages of EK under multiplication by M. Okay? So this is, in fact, so L is the compositum of K adjoint Q with Q any element such any point such that M times Q is in EK. So these are points on K bar such that M times Q is in EK. So it's the compositum of all such fields. we don't know if this is a finite extension yet. In fact, it looks fairly infinite extension of K, but we'll see. It turns out that this is going to be a finite extension of K in some setting. So so here's the compositum of all those fields. So that is the kernel on the right, and hence K or kappa induces what we called a perfect bilinear pairing from EK modulo MEK cross G L over K to EM. Okay, so we have a perfect bilinear pairing. I'll explain what perfect means when we get to it. All right, so again, we are going to, let's start with the well-definedness, and then we'll get through 5 minutes of properties, and we'll continue next time. So proof, first of all, so remember that kappa of P sigma is Q sigma minus Q with Q multiplies by M to P. So well-defined. First of all, remember that M times Q sigma minus Q, that multiplication by M commutes with sigma because multiplication by M is defined over Q. So this was M Q sigma minus M Q, and that is P sigma minus P, which is O, like before. So, so sure, kappa P sigma is an M torsion point, but it is possible that I get a different M torsion point depending on what Q I chose. So for the well-definedness, I also need to check that if I pick another choice of Q, so if Q prime is another choice such that M Q prime is P, then notice that then Q prime is going to be Q plus T for some T of M torsion. This you can prove, for example, if you multiply by M, well, if you can check that there is going to be M, multiplication by M is a degree M square map. There is precisely M square torsion points M. So these Q primes that I wrote, those also multiply to be P, and there are M square of them, so they should be all of them. Okay, so that's one proof. You can also just, I guess, subtract Q prime from Q, multiply by M, and get 0, and therefore Q prime minus Q is a torsion point. All right, so so let's see what happens if I apply the definition of Q of kappa P sigma, which maybe depends on the choice. So I'm going to say this is the kappa defined for Q prime. That would be Q prime sigma minus Q prime. That is Q plus T sigma minus Q plus T. And then if I apply sigma distributed, I get Q sigma minus Q plus T sigma minus T. And here's where it comes handy that T itself is defined over K. So if I define kappa with Q, I get the same result. And here is where I used that the M torsion is contained in the base field, and therefore T sigma equals T for all sigma. All right, so those are going to, that disappears, and I get kappa with Q. Okay, so it doesn't matter which Q I use, I get the same result. Perfect. B, I want to prove that the map is bilinear. First, on if P and P prime are elements of EK with corresponding Q prime, such that MQ is P, Q prime is P prime, then kappa of P plus P prime sigma is going to be, notice that now M times Q plus Q prime will give me P plus P prime. So an M pre-image of P plus P prime is Q plus Q prime. So I can put Q plus Q prime as my Q, sigma minus Q plus Q prime. And if I distribute, this is Q sigma minus Q plus Q prime sigma minus Q prime, and that is kappa of P sigma plus kappa of P prime sigma. So it is bilinear on the left. And so that is on the left. Over on the right. So now I need some sigma and tau in the Galois group, in the absolute Galois group, and apply kappa P of sigma tau. That will be Q with sigma tau minus Q. And then that will be Q sigma minus Q. That's what I wanted to appear, but I need the action of tau also. So I can add and subtract Q tau to the equation to get an equality, and now make Q sigma minus Q and Q tau minus Q appear. Okay, so this is now this is kappa of P sigma to the tau, or with tau acting on it, plus kappa of P tau. But notice again that kappa P sigma is an M torsion point, so it is defined over K, so it is fixed by the action of Galois. So I'm using again to be able to, for this to work, I'm using again that the M torsion is defined over K. So the action of tau fixes things over K, so it fixes kappa P sigma, which is an M torsion point. Okay. Oh, and I'm over time, so I'm going to stop here. So yeah, maybe I'll just write also that kappa P sigma is an M torsion point, and the M torsion point is defined over K, and that's why that was fixed. All right, so next time we will continue with the kernel on the left, the kernel on the right, and get perfect bilinear pairing out of the Coomer pairing. Okay, so I'll stop there.